Can you see the screen?
Yes,
Yes, we
yes.
can see.
Yes, sir.
Okay. So we are starting from first law of thermodynamics. In the last class, which you have seen on YouTube, in the last class, which you have seen on the YouTube, I think you have seen up to first law of thermodynamics. So I'm starting it from there only. Please mute please mute yourself if somebody is there. Okay. So first law of thermodynamics. See, energy can be in two forms. The first one is the energy in transit, that is like heat transfer and work transfer. Somebody wants to join. Just wait. So energy in transit. So the first form of the energy is the energy in transit, like heat transfer and work transfer, and these are observed only at the boundaries of the system or when they cross the system boundary. We have discussed about it. The second is the energy in storage, the energy which will be stored within the system boundary, where energy is stored either macroscopically by virtue of motion, position, or configuration. I think somebody wants to join once again. Yes. Okay. So first law is basically conservation of energy law, conservation of energy principle only. In simple words, we can.
Sir, please check your volume. You are too low, sir.
Hello, am I audible now?
Yes, yes.
Okay. So first law of thermodynamics is basically conservation of energy principle. In simple words, we can say that energy can neither be created nor be destroyed. So that is this basic statement of the first law of thermodynamics. But when we study it on at engineering level, at this particular level, we don't uh, state it in the manner which have been written here in the point number 2 actually. Okay, here we go according to the process, we go according to the system. Okay, only then that's the correct statement of the first law of thermodynamics. So you can see this statement: according to first law of thermodynamics, in a closed system, so remember this, in a closed system undergoing a thermodynamic cycle, so you have to remember these two things: one is the closed system, other is the thermodynamic cycle. The cyclic integration of heat transfer is equal to cyclic integration of work transfer. So mathematically we can say cyclic integral of delta W is equal to cyclic integral of delta Q. Okay. So what is the meaning of this? We will discuss in the next slide. So once again, the first line says FLT is nothing but first law of thermodynamics. Cyclic integral of delta W is equal to cyclic integral of delta Q. Now this is the symbol of cyclic integration. Okay, this is cyclic integration. It's written here, and it is used for a closed path. It is used for a closed path. Okay, it's important to understand it. This is the first law of thermodynamics undergoing a cycle actually. Now let us see the diagram on the right hand side. This is the diagram. This one is the diagram. So what is shown here? We have three processes. This is the process, let us say A process. Here we have the process B, and this is the process C. So the process A is occurring from point number 1, state point 1 to the state point 2, and from state point 2 to state point 3, that is the process B, and from 3 to 1, it is the process number C. So there are three processes. Now what we can do is we can apply this first law of thermodynamics on this cycle actually. And what we can see here is this is the statement. This is what I have written here once again. Okay, or we have written sigma W for the whole cycle is equal to sigma Q for the whole cycle. Sigma means there is summation of the work transfer and the summation of the heat transfers. So I can say that means from this equation of the first law, I can write heat transfer during the process 1 to 2, heat transfer for the process 2 to 3, and heat transfer for the process 3 to 1. This actually is the meaning of cyclic integral of delta Q. So cyclic integral of delta Q means Q adding the heat transfer values for all these three processes, and that should be equal to work transfer during the process 1 to 2, work transfer during the process 2 to 3, and work transfer during the process 3 to 1. So this is the value of delta W. Okay, so that means if I know any five quantities, means suppose I know the heat transfer in all the three processes, and if I know the work transfer in any two processes, I can calculate the work transfer in the sixth process, sorry, the third process. Okay, because there are three processes only, so I will be able to calculate the sixth missing parameter. Okay, now I can also write this in another fashion. I can always say that if I add all these three works, I can always write W net. W net means whatever is the total work which is available to me from this cycle actually. Okay, so I can write W net is equal to Q1 to 2 plus Q2 to 3 plus Q3 to 1. So this can also be said in this particular fashion, that the network which is available in the cycle is given by Q1 to 2 plus Q2 to 3 plus Q3 to 1. Okay, so I hope this is clear to you. One more important point about the first law of thermodynamics is it is accepted as a general law of nature, since no violation of it has ever been demonstrated. So this is nature's law, and we cannot deny it actually. Now let's once again somebody wants to join. So once again, this is the first law of thermodynamics. This is the statement of the first law of thermodynamics, and once again it is used for a closed system, and it is valid for a thermodynamic cycle actually. So this is the first law. Now let us read the heading here. The heading here says the first law of thermodynamics for a closed system undergoing a change of state. When I say change of state, it means I am talking about a process. I am talking about a process. So what will happen in if I am not having a cycle and I am going to look for a process actually, how I am going to apply this first law of thermodynamics for a process now. So let us see once again. What I have written here is this is the statement of the first law of thermodynamics. Cyclic integral of delta Q is equal to cyclic integral of delta W. Now in the next step, what I am going to do is I have brought this delta W on the left hand side itself. So now I can write delta Q minus delta W, and having its cyclic integral here, that quantity will be equal to 0. So it's very important to see here that the right hand side is now 0. So that means I get this particular equation. Cyclic integral of delta Q minus delta W is equal to 0. Now, what do you mean when I say the cyclic integral of any quantity is 0? Okay, here you can see I am saying that cyclic integral of delta Q minus delta W, this quantity is equal to 0. Okay, so what is the meaning of it? The meaning is, if you see the right hand side of this equation, it is 0, and the left hand side can only be 0 if it is a property. It is so because only cyclic integral of a property can be 0 only. So you should remember, we have studied earlier also that if it is a property, in that case, its cyclic integral will be 0. So let us move to the next slide so you would be able to understand it in a better manner. So once again, I have repeated some of the content of the previous slide here. This is the first law of thermodynamics, and I am talking about this particular equation now. Cyclic integral of delta Q minus delta W is equal to 0. And now let us see this example here. What does this example says? If I take the cyclic integral of temperature. Now what is temperature? Temperature is a property. Okay. Temperature is a property. It's an intensive property. And its cyclic integral. Or if I say cyclic integral of dP, what is its value? The value for both these cyclic integrals is 0. Okay, it is 0. Suppose if this is the PV diagram which I am drawing here, PV diagram, if I am say starting from this particular point, point number 1, going up to point number 2, and let us say from point number 2 I am coming back to point number 1 once again. So if I say the temperature here is T1 and the temperature at this particular point is T2, then can you tell me what is the value of the cyclic integral of dt? This will be equal to 0, because now I am the starting point is state point 1 and the ending point is also state point 1. So cyclic integral of dt is equal to 0. Similarly, if I want to calculate the cyclic integral for dp, for the pressure, that will also be 0. And it is 0 because it is a property. Now focus here on this particular equation. Okay, this particular equation, you can see the right hand side is coming out to be 0. So since the right hand side is 0, that means the quantity in bracket means this quantity. I'm talking about this quantity. This should be some property actually. This is a property. Now let us see. Uh, uh, so left hand side should be a property. See, this is what I'm saying actually. Now let us proceed further. You would be able to understand. So same equation once again I have written here, or I can say derivative of this property is equal to 0. Now if I compare this equation and this equation, that means I can always say that this property is actually delta Q minus delta W, or Q minus W. Derivative of delta Q minus delta W is equal to derivative of this particular property. Property, I don't know which property it would be, but yes, I have come to know that this delta Q minus delta W is going to be a property. That is, what I can do is I can write delta Q minus delta W with a cyclic integral is equal to dE. Okay, dE, where E is a property, and this E property is actually known as energy. Okay, it is actually energy, and this energy is nothing but it is the stored energy. So we will discuss about it later on also. So if I remove this cyclic integral sign from both the sides actually, okay, from this side as well as from this side, then I am left with this particular equation. This is the equation now. This is delta Q minus delta W is equal to dE. So this is the equation which is valid for any process, Now this equation is valid for process and not for a cycle. So this is the first law equation for a process. So now suppose I have any process 1 to 2. Okay, suppose this is some diagram, PV diagram, and suppose this is the process 1 to 2, and I want to apply this equation of first law of thermodynamics for a process. So what I will do, look at this equation, and now look here. So what I have done, I have taken the integration for all the quantities in this equation between for the process 1 to 2. So 1 to 2, I am calculating the heat transfer, I am calculating the work transfer for this particular process, and I am calculating the property dE, which I said it is energy. So I can, in the next line, I can write it as Q1 to 2 minus W1 to 2 is equal to E2 minus E1, because E is a property. I can always write E2 minus E1. Had it been a path function, then I could not have written it like E2 minus E1, but it is a property, and we have proved it just now that it is a property. So I am writing it as E2 minus E1. Now this above equation clearly shows Q is the amount of the heat transferred to the system, and W is the amount of the work transferred from the system, okay, during this particular process. The net energy transfer Q minus W will be stored in the system, and this energy in storage, that is E2 minus E1, is neither heat transfer nor work transfer, and is given the name internal energy or simply energy of the system. So you should always remember that the difference of Q and W is actually energy or internal energy. So what exactly it means? Suppose now you should try to understand it. You can see, suppose this is the system here, and let us say this is the Q1 to 2 which is entering the system during a particular process, and let us say the W which is going out of the system, W is leaving the system, okay, this is going out of the system. Then if I say that the value of Q1 to 2 is 30 and W1 to 2 is, let us say, 20, so what will happen to the remaining 10? Difference between this Q1 to 2 and W1 to 2, the 10 will remain within the system, and this 10 which remains within the system is internal energy or the energy of the system. It is internal energy or energy of the system which remains, and you can see it is stored within the system boundary. Actually, it is only the W as well as the Q which is going out of the system or crossing the system boundary actually.
Sir, can you come again on the internal energy? The previous slide.
Okay. uh, okay, I will once again write it in the next slide, so you just see the next slide, you would be able to understand. I said that now there are two equations for the first law of thermodynamics. One is cyclic integral of delta Q is equal to cyclic integral of delta W. This is for a first law of thermodynamics for a cycle. And then I say that now I can also apply equation delta Q minus delta W is equal to dE. This is valid for a process. So both these equations are to be used. This is for a thermodynamic cycle and this is for a process. Okay, what I said is, in the previous slide, what I said is, if suppose if I have this system, and suppose there is 30 joule of heat which is entering into the system boundary, and let us say the work done which is going out of the system boundary is equal to 20. So you tell me, what is the energy balanced here? If I focus my attention on this system here, okay, this is the gas which I am considering as a system. Now how much energy is entering into the gas? It is 30 joules which is entering into the system, and 20 joules which is going out of the system. So that means some part of the energy remains within the system boundaries also. Only then the energy balance will be there, okay, because I am, if 30 is entering and only 20 is going out, that means 10 has to stay within the system boundaries, and this 10 is actually known as the energy or the internal energy. So I am saying that this is the energy or internal energy, and it is stored within the system boundary. So I
Oh,
hope,
okay, sir. Thank you.
okay, now let us once again, I am going to apply this equation which is valid for a process to a cycle actually. Now you see it here. This is the equation which is valid for a process. Now I can also apply it for the cycle, but in a different manner. And this will help me in proving the first law of thermodynamics for the cycle also. Now let us see. If I use this particular equation for process 1 to 2, this is the process 1 to 2, and this is a cycle which I am referring to. So for the process 1 to 2, I can say integral 1 to 2 of delta Q minus integral 1 to 2 for delta W is equal to integral 1 to 2 for dE. And I can write it as Q1 to 2, W1 to 2 is equal to E2 minus E1. Okay, E2 minus E1. Similarly, if I talk about the process 2 to 3, then I can write this equation Q2 to 3 minus W2 to 3 is equal to E3 minus E2. And then if I take the process 3 to 1, then I can write the equation Q3 to 1 minus W3 to 1 is equal to E1 minus E3. Okay, so this I can write. Now what I can do is I can add these three equations. I can add these three equations. So I will get Q1 to 2 plus Q2 to 3 plus Q3 to 1 minus W1 to 2, W2 to 3, W3 to 1. And if you see the right hand side, what do you find? E1 and E1 cancels out. E2 and E2 cancels out. E3 and E3 cancels out. And we get 0 on the right hand side. And this validates the equation of the process also, because using the concept of the process we have applied this for the cycle also. We have applied this equation for the whole cycle actually. And what do you get? You get this particular value, that total sum of heat transfer minus total sum of work transfer comes out to be 0, which is nothing but the first law of thermodynamics for a closed cycle. Cyclic integral of delta Q is equal to cyclic integral of work. So basically, we have proved using the first law of thermodynamics for a process that this equation can also be used for a closed cycle actually. Okay. Now there are different forms of the stored energy. I will not go in much detail about it. I will just come to the conclusion of it. Okay. I will come here actually on this particular slide actually. Now you just remember that this is the equation delta Q minus delta W is equal to dE. So now I am going to tell you what is this E actually. This E is energy of the system. This is the energy of the gas, or yeah, because we are talking about the gas here, so I can say it is the energy of the gas within the system boundaries actually. Okay, within the system boundary. So what is this E equal to? This E is actually equal to, this is the kinetic energy part of the molecules. This is the potential energy of the molecules, and this is the internal energy of the molecules. And this is microscopic in nature. That means the internal energy is microscopic in nature, whereas the kinetic energy and potential energy, we are taking it as the of the whole molecules, and it is the macroscopic energy. But you should not worry. You should just remember that this E is actually equal to, this is the kinetic energy part which is given by mv square by 2. This is the potential energy part which is given by mgz, and this U is the internal energy. And I can also say that I could have written this U as m into small u. When I have written it here as the capital U, it is total internal energy. It is total internal energy, and its unit is either joules or kilojoules. Okay, but when I am writing here small u, this small u stands for specific internal energy, and its units are either joules per kg or kilojoules per kg. So I hope this is clear. So basically, E is nothing but E can be said to be equal to capital U plus kinetic energy part plus potential energy. Okay. And if I say that the kinetic energy is zero, potential energy is zero, in that particular case, we are left with E is equal to U. So in most of the cases, we would be using the equation delta Q minus delta W is equal to du. So this is the equation of the first law of
Teacher,
thermodynamics. Yes.
and why we consider as E key equals zero and E peak equals zero?
See, normally these will be very small. If we are considering that these are small, what I have written here, if you read here, in absence of motion or gravity, see the motion gives rise to the kinetic energy and gravity gives rise to the potential energy. So that is why we are considering it negligible also. Okay, so we are considering them to be negligible in comparison to the internal energy. So I am left with this particular equation. So if you are, you can either use this particular equation delta q minus delta w is equal to de, or you can use delta q minus delta w is equal to du. Both are the equations, these are valid. But in most of the cases, when we are solving numerical problems, you may not be given with the values of the kinetic energy and the potential energy. So you don't have to worry about that part. The kinetic energy and the potential energy will be considered negligible. Okay.
Okay,
So
okay,
let us proceed further. So finally, I can say that this is the equation delta Q minus delta W is equal to du in the absence of kinetic energy and potential energy. Now, what is U? U, capital U is a extensive property called as internal energy, whereas small u is equal to capital U divided by mass, where small u is specific internal energy. And here I have once again written the SI units for U in total internal energy or only internal energy. The unit is kilojoules, or you can also use joules. And for small u, it is kilojoules per kg, or you can also use joules per kg. Okay, so this was about the units. Now, let us go to the. This was about the first law of thermodynamics. Till now, we were talking about the first law of thermodynamics, and we have discussed about two equations. The first one is cyclic integral of delta Q is equal to cyclic integral of delta W, and the second equation that we have used is for the process delta Q minus delta W is equal to dE or du. Depends upon the values. If we are given with the kinetic energy and potential energy terms, then we can use dE, otherwise we will use du. Now, in thermodynamics, in most of the cases, when we are talking about the ideal gas, actually, when we are talking about the ideal gases or the perfect gases, Joule's law states that internal energy is proportional to temperature. So this is the equation. U, or the internal energy, is proportional to temperature. Or if I remove this proportionality sign, then I can say that this U, now it is small u. Okay, small u is equal to Cv into T. Okay, and this Cv is actually constant and is known as the specific heat at constant volume. We have discussed about the specific heat at constant volume as well as specific heat at constant pressure also. And this small u is the specific internal energy in kilojoules per kg. So don't worry, it is not at all difficult. I am saying that U is equal to Cv into T. This is the equation which you need to remember. And if I write it as capital U means total internal energy, what I will do, I will multiply it by the mass, and this is the specific internal energy. So I will get this equation because this small u is given by this value CVT. So m into CV into T. In other way, I can also write as that capital U is nothing but it is equal to m CV T. And if I write this equation in the differential form, okay, we can say du is equal to mcv dt. And if I integrate this equation between state points 1 to 2, okay, then m and cv being constant can be taken out of the integration sign. You can see it here, and when I will integrate dt, I will get t2 minus t1. So the left hand side, u being a property, can be written as u2 minus u1 is equal to mcv t2 minus t1, and this u2 minus u1 is change in internal energy. So this is change in internal energy given by mcv t2 minus t1. Okay. So this is Joule's law. Once again, to remind you, it is valid for ideal gases. Okay, ideal gases, not for the real gases. There could be real gases also. Real gases behave in a real manner. It's not all gases are real gases. They are not the ideal gases. Okay, and you know, for the ideal gas, we use the equation PV is equal to MRT. Okay, so now let us proceed to the next topic, heat transfer in various processes. Now, one thing I would like to make you aware, that is, one, we have already calculated the value of PDV work. We have already calculated the value of PDV work. And now I have calculated the value of change in internal energy, that is du. And I know first law of thermodynamics, if I say I am going to talk about the processes, you know about the various processes. These are pressure is equal to constant, temperature constant, then volume constant, reversible adiabatic process, then polytropic process, PV raised to power n is equal to constant. And for all these processes, we have calculated the value of PDV work. Okay, this has already been calculated. And now we have just introduced the concept of change in internal energy, which is given by mCV T2 minus T1. This is the value of change in internal energy. And we have just discussed about the first law of thermodynamics also for a process, which is delta Q minus delta W is equal to du. So if I want to calculate the heat transfer, then it would be equal to du plus delta W. Now this delta W, when I am talking about, this is actually PDV work. This is actually PDV work. Okay. If it is not a PDV work, there can be actually different type of the works. For example, we discussed about number one PDV work. We also talked about shaft work. Okay. We also talked about paddle wheel work. Okay. We also talked about flow work, and there could be another type of the work also, like magnetic work. Okay. There could be electrical work. So there could be, please mute yourself. Somebody's mic is on. Please mute. Okay. So, but when I say heat transfer in various processes, I am just interested in considering the PDV work only. So we are going to think about the PDV work only. So let us see how we can derive the equation of the heat transfer for the various processes. Now this is the first process which I am considering here. I am considering about heat transfer in a constant volume process. So my focus is on now constant volume process or isochoric process. So for a constant volume process, V will be 0. So once V is 0, V is constant rather, when volume is constant, we know what is the value of the PDV work. PDV work is 0 in a constant volume process. And this is the PV diagram for that particular case. You can also draw this process in this fashion also, from 1 to 2, vertically going upwards or vertically going downwards. Anything is possible. And what is the gas equation? I told you I am going to calculate the heat transfer for a ideal gas only, okay, which is undergoing various type of the processes. So this is the equation. Once V is constant, if the V goes, so V is constant, so I can say P by T is equal to Mr divided by V. So Mr is constant for a gas. This is already a constant, and this is also constant. Volume is constant during the process of isobaric process. So I am left with T by P or P by T is equal to constant, or I can say pressure is proportional to temperature, and this is known as Gay-Lussac law. This is Gay-Lussac law. And if the process is taking place from point number 1 to point number 2, I can write this equation that P1 by T1 is equal to P2 by T2 is equal to constant. So I am giving you the whole information now about the process actually. Okay, so for a constant volume process, work is 0, and this is the PV relationship. Okay, this is the PV relationship. Now the change
Sir,
in,
kindly repeat.
see, I am interested in calculating the heat transfer of this constant volume process. So I am giving you the whole information about the work transfer, internal energy, what is the PVT relationship. Okay, PVT relationship. What is the relationship between pressure, volume, and temperature in case of a constant volume process? The volume being constant in this particular case, if I apply this here, PV is equal to MRT. I can write P by T is equal to MR by V. M into R, this quantity is constant for every gas. Okay, suppose if I take this as the system, there is a particular mass of this gas, okay, and for this gas we have a characteristic gas constant R. So that means if the mass of the gas is constant, then R is also has a particular value. So M into R, this value M into R will be a constant, and during the process of constant volume, V is also going to remain constant. So it's a constant divided by a constant, so I can always say that P by T is equal to constant. So this is the PVT relationship in a constant volume process, and then I can extend this P by T to this particular process 1 to 2, and I can write this equation: P1 by T1 is equal to P2 by T2. Now I can write the change in internal energy now. U2 minus U1 is equal to M CV T2 minus T1. You know that the mass unit is kilograms, CV it is kilojoules per kg Kelvin, and temperature is taken in kelvins only. So you can see when we multiply all these terms, kg will cancel out, Kelvin will cancel out, and we will be left with only kilojoules. So this is the value of change in specific internal energy here, because the mass was multiplied on the right hand side. So this is total internal energy, change in total internal energy. Here it is specific, here it is specific, because we are using small u and there is no m actually, m is missing here. So now we can calculate the value of heat transfer for this constant volume process, and we can use this particular equation: delta Q is equal to dU plus delta W. Okay, we know the value of dU, we know the value of delta W. We can just put these two values here, and we can know the value of the heat transfer in a constant volume process. So once again, same equation. So what is the value of delta W or W? This is equal to 0. Okay, this is 0. So once this value is 0, delta Q will come out to be equal to du, and you know the value of du is given by mCv T2 minus T1, which is equal to U2 minus U1. So for a constant volume process, the heat transfer in a constant volume process is equal to change in internal energy U2 minus U1. So this is the final conclusion for this particular case. Now let us proceed. Yes,
Teacher, teacher,
yes,
teacher. It means we can write du equal heat plus work.
yes. See, this is the first law equation. See, we this is the equation delta Q minus delta W is equal to du. This is the first law of thermodynamics for a process. Okay, from this equation I can get delta Q is equal to du plus delta W. And because in constant volume process this value is 0, so we are left with this particular equation. So when I will integrate this equation, delta Q from 1 to 2 equal to del du from 1 to 2, I will get Q1 to 2 is equal to mCV T2 minus T1, because this du can be written as mCV dt. Okay, is it clear?
Yeah.
Okay,
Yes. Yes.
okay.
Yes, teacher.
So now let
Thank
us
you.
proceed to the heat transfer in a constant pressure process. So once again, this is the equation of work transfer for a constant pressure process. It is given by P V2 minus V1, P being constant. Okay. Now I am interested in finding out what is the PVT relationship. So I am interested in calculating PVT relationship. I know this is the gas equation. PV is equal to mRT. Okay. And P being constant can be taken on the right hand side and temperature can be brought to the left hand side. So I am left with V by T is equal to mR by P. And the right hand side term is now constant. So I can say that V by T is equal to constant. Okay. And otherwise I can also say that V is proportional to T. And what is this law known as? Does anybody know? What is this law known as in chemistry? You must have studied it. It is Charles' law.
Out,
Gas
yeah.
laws.
Is it
Charles'
both?
law. Okay. So now this is the constant pressure process 1 to 2. And if I want to apply this equation, V by T is equal to constant for this particular process 1 to 2, I can write V1 by T1 is equal to V2 by T2 is equal to constant. Okay, now this is the next slide. Now once again, change in internal energy, if I want to write, I can write this particular equation, change in internal energy, mCV T2 minus T1. And this is the equation for the heat transfer from the first law of thermodynamics, which is given by delta Q is equal to delta W plus du. This is valid for a, you remember it is valid for a process. Okay, so I can put the value of 1 W2, which is P V2 minus V1. U2 minus U1 is given by mCV T2 minus T1. So we can add this and we can get the value of heat transfer. And you know, PV,
Teacher, teacher,
yes,
why we
tell me.
didn't put CP? We are in constant pressure. We put MCV. Why?
See, listen,
Here, you
listen to me. See, this is change in internal energy. Okay,
no.
this change in internal energy, I have told you the law says, the Joule's law says that U is proportional to T. And when we remove this proportionality sign, U is given as CV into T. This is the value of the internal energy. And if I write this in the differential form, I write it as dU is equal to mCV dt. So you think of any process, you talk of any process, this change in internal energy will be given by this particular equation only. You cannot use any other equation. So du is always equal to mCV dt. There is no question of Cp in that particular case. Okay. So I can write work transfer as PV2 minus V1 here, and change in internal energy as mCV T2 minus T1. And you can see here it is PV is equal to mRT. So instead of PV I can write mRT. So here you can see PV2 can be replaced by mRT2 and PV1 can be replaced by mRT1. So you can see now this T1 minus T2 minus T1 is here and T2 minus T1 is here also. So you can take this M and T2 minus T1 as common. You can take it out of the brackets and you are left with R plus CV. So this is R plus CV. So once you must be remembering R plus CV. the Cp minus Cv is equal to R. So if you calculate Cp will come out to be R plus Cv. Okay, and you will get the value of heat transfer as mCp T2 minus T1.
Yeah, that's nankola no kalekale. Beg fizzy.
Uh, is somebody asking any something? Asking something?
No.
Oh, I think there is a background noise actually. Okay, so heat transfer for the process will be given by mCp T2 minus T1. So once again, I can tell you if I calculate for the constant pressure process, W is given by P V2 minus V1. If I calculate change in internal energy for constant pressure process, it is given by mCv T2 minus T1. If I have to calculate the value of Q, it is equal to mCp T2 minus T1. And this is actually nothing but the sum of W1 to 2 and U2 minus U1. Okay. And what is Cp?
Yeah.
Cp is the
Yeah.
specific heat at constant pressure. So I will end my lecture here. It is already uh, near
It's what
3.
I was asking.
Yeah, yeah.
It's
See,
what it's that.
yeah, I was knowing it that it will come in end. But when you talk about
Uh,
internal energy, you always have to take CV. So this was to come actually. Okay. So I think this is clear to you.
okay.
Now I will end my lecture here.
Yes.
Just wait. Let me take the attendance.
Okay. There, there is no a recommendation to do.
What means something next which you have to do? You are asking about that?
Yes.
I will give you some assignments.